All right, so last time we talked about fast Fourier transform, and we talked about expanding everything in Fourier basis. So if you remember there was this idea of spectral methods. In particular, we talked about using cosines and sines as our basis. And when you use cosines and sines as your basis, you can have periodic boundary conditions, no flux boundary conditions, pinned boundary conditions. Okay? And the key there was to say what we want to do is transform somehow our data in this spatial domain over into a frequency representation of this. It's frequency representation because when we transformed it to cosines and sines, what we were really doing is writing in terms of the wave numbers of those cosines and sines. And at first, this operation was going to cost us order n squared. So it wasn't saving us any time, really, until what we found is through this Cooley-Tukey algorithm of the fast Fourier transform, this thing here dropped down to that. And ultimately, this is why the FFT is used everywhere. It's so hard to come by that kind of speed on a computation. N log n is about as good as you can get. And if you can write down algorithms that beat n log n, you will have a name attached to it, and you'll be very famous. You get a job wherever you want. Okay? That's as easy as it is. That's all you got to do is beat n log n. You see how easy it is? I'm giving you the keys to success today. All right. All right. Now, cosines and sines aren't the only thing we could represent in. Remember, the idea of spectral is that really what you did here, there's a philosophical shift, which is before, when we were doing finite difference, remember, we chop up the domain to a certain number of points. We're going to evaluate whatever our solution is on these points. And when you do finite difference, the way you think about doing derivatives, the way you do everything is by using your neighbors. Right? You break it up, and if I want a second derivative here, I need a neighbor over here, a neighbor over here, twice myself. So everything is a local calculation. This point here cares only about its neighborhood. When you do cosines and sines, now the expansion is in a global basis. These cosine and sine modes live on the whole domain. And you're going to represent everything in terms of these cosine and sine bases, which are global. Okay? There's a big shift in how you think about this thing. And you get big accuracy gains by doing so. Now, there's no reason that cosines and sines have to be special. There's a lot of different things you could expand in besides cosines and sines. And in fact, if you, and especially in the early 1900s, late 1800s, people had all these what are called special functions. And I'll drop some of them on you here today. Okay? And they're just really, it's the same idea as cosines and sines. And let me give you some examples. Bessel functions. Many of you have probably heard of Bessel functions. When do you use Bessel functions? Well, there's a very specific place where you use Bessel functions. Basically, you use them on radial 2D problems. Actually, just put radial 2D. So, for instance, a vibrating drum head, if it's a circular domain, that you're going to try to calculate how this vibrating drum head, what are the modes, what kind of sounds you can get on a vibrating membrane, you would use Bessel functions, or the natural basis for this. Okay?
Does that mean you start in the middle, or
no. In fact, this here, you can hit the edge of the drum because you have asymmetric modes in the Bessel functions. So, for instance, let me just draw a picture. There's my drum head. One mode could be just vibrating like this. Right? A mode like this. Right? These are all Bessel functions. Right? And then you can cut that in half. These are all the sort of behaviors you'd imagine. And if I hit anywhere on this drum head, it excites a number of these modes. Okay? So that's the typical drumming. In fact, if you've ever played with a drum, right, as you hit in the middle versus go out to the edges, it does make different sounds because you're hitting different things. A very famous paper, by the way. Can you hear the shape of a drum? If you were to hear a drum, could you reconstruct its shape? Just by knowing, here are all the frequencies I hear, could I go back and make up what the domain looks like? The answer is hard because it's not unique. But it's a kind of a cool, that was a famous paper. You can look it up on Google. It's not on YouTube yet, but here's the shape of a drum. Here's another special function, Legendre polynomials. And these are for 3D Laplace equations. So for instance, you may have heard of this from electromagnetic theory. So when you're looking at three-dimensional structures, Legendre polynomials are sort of the way you might reconstruct or construct these things, okay? Gauss Hermite, which you are already familiar with. This is Schrödinger with a harmonic potential. So I'll put harmonic quantum mechanics. Gauss Hermite functions were what we wrote down in class, what you did in homework 2, 1, 2, 2, 2. Homework 2, when we wrote those down, you get them right out of the textbook. That is a natural basis to expand, because these are the natural solutions of the system where it has this parabolic potential sitting in it. These are just these Gauss Hermite polynomials. You can write them down, and you could use them. Spherical harmonics. It'd be nice to spell sphere correctly. There we go. Spherical harmonics, and of course these are now radial problems, 3D. So they're like Bessel functions, except for now they have this extra dimension. Spherical harmonics play a role in quantum mechanics, for instance, and they're just a generalization of these structures here. Instead of on a membrane, now you're in a ball, and you're looking at the vibrating modes of the ball, if you'd like to think of it that way. Okay? So here's all these special functions. And in some sense, it highlights a philosophy that people had very early on. Right? These guys, as you reckon, hopefully you see these names. These are guys from in the past who were, there's a lot of these French mathematicians in the 1800s who were very wealthy, who sat around doing math. And then they did some interesting stuff, and then they got their names on these things. But back then, they were solving differential equations. There was no computer. And they were looking sort of, in some sense, for the natural way to express solutions of these problems they were looking at. They came up from a variety of places, and they came up with these special functions. There is actually nothing special about the differential equations. It's just that these differential equations kept coming up over and over and over again. And whoever's working on it said, oh, well, that equation keeps popping up. Let's give it a name. Call it a Bessel equation. Call it Legendre's equation. So these are all special functions. You can find whole books on just special functions. And there's mathematicians who specialize on special functions. Okay? So the question is, why not use those? What's so special about cosines and sines? The only difference between cosines and sines, and why it isn't lumped with all of these, is that you can do that to it. These are all order n squared. Take your data and represent it in terms of these functions. It's a natural thing to do. It'll cost you order n squared. Okay? The beauty of this, but why don't they have the FBT, fast Bessel transform, or the FLT? Because none of these you can, remember, this had a very special structure that allowed you to relate different components of the matrix when you took the transform, which then allowed you to break the problem up into 2 problems of half size, and then 4 problems each of half size of those 2 half size problems. And that's how you were able to get that kind of speed.